The wavelength associated with ordinary objects or objects are in our daily life is so small that is beyond any measurement. This is the reason why macroscopic objects in our daily life do not show wave-like properties. On the other hand, in the subatomic domain, the wave character of particles is significant and measurable. This means ordinary object has very small wavelength and it is not measurable. So we cannot observe wave nature of such particles. That is why we are not bothered about the wave nature of such particles. Consider an electron of mass m and of charge E accelerated from rest through a potential V. The kinetic energy K of the electron equals the work done EV on it by the electric field. K is equal to EV. Now K is equal to half mv square or K is equal to p square by 2m. So that P is equal to square root of 2mk or which is equal to P is equal to square root of 2mev. The de Broglie wavelength lambda of the electron is then lambda is equal to h by p, which is equal to h by square root of 2mk, which is equal to square root of 2mev. Substituting the values of h, m, e, we get lambda is equal to 1.227 divided by square root of v nanometer, where v is the magnitude of accelerating potential in volt. For a 120 volt accelerating potential, this equation gives you lambda is equal to 0.112 nanometer. This wavelength is of the same order as the spacing between the atomic planes in crystals. This suggests that matter waves associated with an electron could be verified by crystal diffraction experiment analogous to X-ray diffraction. We describe the experimental verification of de Broglie hypothesis in the Davison-Germer experiment. In 1929, de Broglie was awarded the Nobel Prize in Physics for his discovery of the wave nature of electrons. So this suggests that electrons can be imagined as associated with the wave nature, or electrons possess a wave nature, or electrons may be assumed to be waves. So this suggests that electrons may consider as a matter wave. Thus electrons, those particles can be attached to the properties of matter, and this matter deals with the waves in general. The matter wave picture elegantly incorporated the Heisenberg uncertainty principle. According to the principle, it is not possible to measure both the position and momentum of an electron or any other particle at the same time exactly. There is always some uncertainty delta x in the specification of position and some uncertainty delta p in the specification of momentum. The product of delta x and delta p is of the order of h cut, that is h by 2 pi. We can write that delta x into delta p is approximately equal to delta h. This equation allows the possibility that delta x is 0, but then delta p must be infinite in order that the product is non-zero. This means delta x, that is the position in uncertainty, we are sure that where is the particle is located, but it gives the fact that then delta p, the uncertainty's momentum is become infinite. Commonly, delta x and delta p are non-zero such that their product is of the order of h cut.